This is a question from one of the FWC papers from 2015, FWC 2015, November, grade 13, right? So this question is about thermodynamics. Pretty much covers a lot of aspects from thermodynamics, I think the latter part is about gas laws. Let's get on to the question very quickly. A part, let's start with A part. Write the first law of thermodynamics in mathematical form and identify its terms. Number one, it's pretty straightforward. Delta Q equals delta U plus delta W. Now, what is delta Q? Delta Q in first thermodynamics is heat exchange. Heat exchanged. Heat energy exchanged. It could have been absorbed by the system or it could have been released from the system. That is the heat energy exchange. Delta U is a change in internal energy. And delta W, we know it's work done. Right, time dusted work done. Good. So that's it, finished. And then we move on to number two. What does it say? Explain isothermal process and adiabatic process. Now, talking about isothermal process, in the isothermal process, change in internal energy is zero. So I'll say delta U is zero. So if you put that into words, you will say change in internal energy is zero, or a process which takes place under constant temperature. You can say that also. Yeah. So you can say there's no change in internal energy during that process, or temperature is maintained constant throughout the process. That is it. And adiabatic process, talking about adiabatic process is a process where the net heat change from or in the system is zero. The net heat change in the system is zero. That is adiabatic process. All right. So I've just written in symbols. You can put that into words. And the third part now, they're asking for the conditions. State the conditions needed for isothermal process and adiabatic process. Now, for isothermal process, we don't want the temperature to increase or decrease. Therefore, it has to be a slow process. The process has to happen slow. Slow process at constant temperature. I can say that way, right? Slow process at constant temperature. So that's going to be an isothermal process. And adiabatic process, adiabatic, net heat change to the environment, between the environment and the system must be zero. That means it should be a rapid process, a very quick process. There mustn't be any time for heat exchange to happen. All right. So these are very straightforward theory parts, and these are the fundamentals of this first law of thermodynamics. And delta Q can be plus and minus, delta U plus and minus, delta W plus and minus. Those things you can check from the theory. Right. And then moving on, let's move on to the B part. Now we are done with A part, right? And B part. And they have given us a graph, so I'll start B part here because I can work with the graph conveniently. Yeah, B part. So what does B part say? An ideal gas is undergone a cyclic procedure of ABCA as shown in the figure. Internal energy of gas at A and B are 20 joules and 50 joules. Okay, they have given the internal energy UA. So internal energy at A is 20 joules. Internal energy at B is UB, that is equal to 50 joules. Okay. Heat absorbed by gas during BC process is 90 joules. Heat absorbed by the gas during BC. So here, delta Q BC, that is equal to heat is absorbed. So delta Q is positive there, plus 90 joules. Okay, good. What is the internal energy of gas at position C? All right, let's start with that, Roman 1. I'm talking about that question. If you take process BC, it happens at constant volume. Okay, it happens at constant volume. So for process BC, you can say delta V is zero, constant volume. Okay, constant volume. It's constant volume process. If the volume is constant, change in volume is 0, like I have mentioned above. If the change in volume is 0, then we can say delta W is equal to 0. If delta W is 0, if you go back to the first law of thermodynamics, delta Q is equal to delta U plus delta W. If delta W is equal to 0, I can say delta Q should be equal to delta U. Now, what is delta Q for process BC? That is plus 90. I'll just put 90 here. And what is delta U? Delta U is internal energy at C, final internal energy minus initial internal energy. That is UB. Now 90 is equal to UC is what we are supposed to find out, minus UB is 50 joules. Therefore, internal energy at C is going to be 140 joules. 140 joules. So 140 joules is the answer. And then let's move on to the second part. What does it say? Roman 2. What is the amount of heat absorbed by the gas during process AB? During process AB. Good. Now, talking about process AB, first, okay, process AB. Let's find out the change in internal energy, delta UAB. So, how do you find that? Final internal energy minus initial internal energy. And that is UB is how much? 50. UA is 20. Minus 20, and that is plus 30 joules. Plus 30 joules. That is a change in internal energy. And also you can find the work done, delta WAB. And work done during by that portion is given by this area, isn't it? Area under the curve. Area under the curve. This area will give us work done. Okay, that's that can be conveniently found out. How is that? This is a rectangle, isn't it? 10 into 2. 10 into 2. Volume is in meter cubes. Pressure is 10 Newton per meter squared. So it's 10. Yeah, 10 into 2. 10 into 2. That is equal to 20 joules. And that is it plus or minus? It has to be plus 20 joules. I forgot to put that. Plus 20 joules. Why did I put plus? The plus is because volume is increasing. Volume increases. If the volume is increasing when you go from A to B, you have to consider the work done as positive. Right. I think we have everything we need. We can apply this equation, delta Q AB from process A to B. I'm applying first law of thermodynamics. This. Right. So delta QAB is what we are supposed to find out. Delta UAB is given by 30 plus 20. Final answer is plus 50 joules. So 50 joules of energy is absorbed by the system. Third, Roman 3. Does gas absorb or release heat during the process CA? What will be the amount of heat absorbed or released? All right, that's interesting. We need to find out Roman 3. So for that, we have to know the internal energy change first of all. Now, UC was found out. How much was UC? 140. UC is 140 joules. Okay, right. So, yeah, I think we can finish it. No problem. Let's start the third part of question B. Third Roman 3, question B. Right. First and foremost, now we are talking about process CA. I'll find out delta UCA. Delta UA, starting with that. So that is UC minus UA. Sorry, UA minus UC. Final minus initial. UA minus UC. UA minus UC. UA is 20. It's already given in the question. 20 minus UC is something we found out. That is 140. 20 minus 140 is minus 120 joules. And we can find out the work done. Delta WCA. Work done will be the area under line CA. Area, the whole area under the line CA. Okay, so that's going to be a trapezium. How do you find the area of the trapezium? Half into the length of the parallel side. So you have to find the whole area under CA. Okay, because it's a process. So if you want to find the work done during a process, you have to find the total area under that particular line, just like we did. So, right, fine. Okay. So half into the addition of parallel sides will be 10 plus 30. You can see this is one side of the trapezium we are talking about. This is a trapezium. Right? This is a trapezium for work done. Right. And this is the other side. So 10 plus 30. 10 plus 30, and it must be multiplied by the height, and in this case the height is 2, this one. 3 minus 1, 2 into 2, and I think that is 40 is the answer I'm getting, 40 joules. But you have to be a little careful about the sign. Volume is decreasing when you go from C to A. Volume is decreasing, therefore it's negative. Okay, it's negative. Why did I put negative sign this time? Because volume is decreasing. Volume decreasing. Right, that's it. Now, again, you know what to do. You can go for first law of thermodynamics quickly. Delta Q CA is equal to delta UCA plus delta WCA. All right. So what is delta QCA? That's what we are supposed to find out. And what is delta UCA? That is minus 120. Delta WCA is minus 40. Therefore, the answer is minus 160 joules. So you can say 160 joule will be released. That's what they're asking. Released by the gas. Let's move on to C part. In an insulated cylinder gas is filled and closed by a smooth piston as shown in the figure. Cross-sectional area of the cylinder is 8 into 10 to the power minus 3 meters square. Helium gas is filled in the cylinder at a pressure 1 into 10 to the power 5 Pascal and temperature 27 degrees Celsius. Now, we normally apply the equations and laws for ideal gas. Now, helium is in an inert gas which resembles a lot with ideal gas. It has a lot of, it shows a lot of similar properties. Now, helium has a very light mass, so the intermolecular interaction is very weak. It is spherical in shape. It does not react with other, molecules or elements. So a lot of similarities are there. That's why they have gone there. And heat temperature is 27 degrees Celsius. Height of the gas column is 30. So they have given us the area and the height so that we can find the volume and heat capacity of cylinder and piston negligible. First of all, find the number of moles of helium in the cylinder. Okay, how do you do that? Find the number of moles. Start C part here, right? When you want to find the number of moles, you have to obviously go for PV is equal to nRT, or else can we do it in another way? Yeah, we know everything. So it's just, then you can say number of moles is equal to PV over RT. PV over RT. Right, now we have to carefully substitute the values. N is equal to pressure 8 into 10 to the power minus, no. Pressure is 1 into 10 to the power 5. Volume is area multiplied by height. Area is 8 into 10 to the power minus 3. Height is 30 centimeters. So it should be 30 into 10 to the power minus 2 divided by R is 8. They have asked us to take it as 8. So we have the liberty. It should be joule per Kelvin per mole. There's something missing here. Joule per Kelvin per mole. Into temperature is 27 degrees Celsius. You can't put 27. It should be 300 Kelvin because when you substitute, you should substitute in absolute temperature, 300 Kelvin. And then the number of moles will be, if you simplify this, a lot of things can be simplified in this. A lot of things will get cancelled out. Now 10 to the power 5 can be cancelled out with these two, right? 8 can be cancelled out. I have 3 over 30 and that's obviously 0.1. 0.1 moles is the number of moles. All right, that's done. That's the first part, Roman 1. And then Roman 2 part. What is it? Find the root mean square speed of the molecules of helium in cylinder, right? I'll do it here. Roman 2. Roman 2, root mean square speed. So read the question carefully. It says root mean square speed, that is root mean square speed. That is equal to square root of 3RT over capital M. So that's going to be equal to square root of 3 into, for R we can put 8 into, for T we have to put 300, and you have to divide it by molar mass of helium is 4 grams per mole. 4 grams per mole. So you should substitute 4 into 10 to the power minus 3 kilograms per mole because R is in SI units. So capital M, molar mass, should also be substituted in SI unit. And if you simplify that, what will you be getting? We'll be getting, it's weird, right? 2 into 9 into 10 to the power 5 square root. 2 into 9 into 10 to the power 5. So I'll take it like this. 20 into 10 to the power 4. So I'm getting square root of 20 into 3 into 100. Hope you can understand this. From this 10 to the power 5, I borrowed a 10, so it's 20, square root of 20. Square root of 9 is 3. Square root of 10 to the power 4 is 10 to the power 2. All right. And this is square root of 20 can be written as 2 root 5 into 3 into 10 to the power 2. For root 5, you can put around 2.25 or something like that, 2.25. Let's substitute that. And then it's 6 into 2.25. 6 into 2.25. 6 into 225. I'm getting something around 1350 meters per second. Roughly, answer around that. Find the number of moles. Shit.